And now we arrive at our final section, the final 20-question stretch here of our June 2018 Physics Regents. In this section, you're going to have question sets that are grouped together typically by topic, and in this case, answers will carry over from the first question down to the following questions. And in that case, what happens if you get something wrong in the first question? You're going to have to carry that error throughout. But the beauty of this in the grading rubric is that you can still earn the full credit for the later questions so long as you carry out your calculations properly. If you carry over the answers in the correct method, despite how wrong your numbers might be. You will lose points in your earlier mistake, but then the rest of it, as long as you do everything correctly, you'll get the full points later. And we start with a light bulb question with circuits and resistance. And here, for numbers 66 to 67, we need to calculate the cross-sectional area of this tungsten wire filament. So this relates to resistance in a wire type question. So A is question mark. We need L. The L value is right here, 0.22 meters. We also have a resistance R value of 19 ohms. The material of our wire is tungsten, so we need to look up the rho value on the reference table because we're going to use this equation. R equals rho L over A. That's not a P, it's rho, the Greek letter rho. So I'm going to pull up the reference table to show you. Okay, so this you'll find in the electricity page of your reference table. Here they'll have the resistivity values. 20 degrees is not really necessary. They'll always state it in your question as a formality's sake, just so these values are valid to use. And the only thing we're concerned about here is finding the rho value for tungsten. And that's 5.6 times 10 to the negative 8 ohm meters. So you need this unit for your substitution step for your calculation work. Okay, so let me get rid of this. 5.6 times 10 to the negative 8, that's our value. Now we just have to substitute our values in. 19 ohms equals 5.6 e negative 8 ohm meter times the length of 0.22 meters divided by A. So this is where the algebra can get tricky. Make sure you're bringing that variable up to the top, multiplying 19A equals the numerator of your fraction so you can do the algebra correctly. Because especially when you're missing variables in the denominator, that's when the algebra gets messy. Okay, and you get a cross-sectional area of 6.48 times 10 to the negative 10 meters squared. So that's a really small cross-sectional area. We're used to seeing a lot of cross-sectional areas that are 1,000 times bigger to the negative 7 range. But in this case, we have a very small one. All right, number 68. Explain why the resistance of a tungsten wire filament increases when the bulb is being operated compared to the resistance of the filament at 20 degrees Celsius. Why does it increase? Well, let's say we connect it to the circuit and the bulb is now turned on. What do you usually feel? You feel heat. So when the circuit's turned on, there is heat being radiated and higher temperatures lead to higher resistance. So if you want to explain this in the shortest concise statement, in the most concise way possible, you could just say the temperature has increased. The temperature is higher or it has increased. And that's the shortest way you could explain why the resistance is higher, because the temperature is higher. Number 69 to 70, calculate the power of this light bulb when it is being operated at a potential difference of 120 volts. We have to show all work. So we need to calculate for power. We have a potential difference of 120 volts. We also have resistance R. So it's got to be V squared over R is our equation for power. There are multiple power equations you could use, but given we only have voltage and resistance, we got to use this version. So this is going to be 120 volts squared divided by, now careful because they give us two different resistance values. So when the wire filament was originally at 20 degrees Celsius, it had a resistance of 19 ohms. But once you connect it to the circuit, it now raises the resistance to 240 ohms with the 120 volts. And so for this particular question, since we're focusing on when it's being operated, we're using this R value of 240 divided by 240 ohms. All right, 120 squared divided by 240. You get a value of 60 watts as your answer. And that's it for this part. Okay, now 71 to 75 has a forces question with friction involved. Okay, now we have a wooden crate on a wooden floor being pulled at 150 newton force at an angle of 30 degrees, and it's moving at a constant velocity. So there are a lot of important keywords here to definitely help make our problem easier, and we just got to remember those keywords and how they are applied. So to start, we have 71 to 72. Calculate the magnitude of the horizontal component of the 150 newton force. So we just need the horizontal component because it's at an angle of this force vector. The equation you can use on your reference table is AX equals A cosine theta. A represents the vector quantity. AX is the horizontal component of that vector. So we're looking for AX. A is our vector quantity. That's 150 newtons because that's the vector we're focusing on. Cosine of the angle 30 degrees. In your calculator, you'll probably get 129.9, or you could round it up to 130 newtons. Either one's okay, as long as you know how to round accordingly. So 130 newtons is the answer for this part. Now, 73, determine the magnitude of the frictional force acting on the crate. We don't really need to calculate anything. We don't have to show work. It's only 1 point. And this is where answers carry over, because what we got, 130 newtons, is going to be important to helping us answer number 73. Okay, let me draw stuff here. This force, 130 newtons, is the one that's being pulled along. Let me draw that to scale. Okay, 130 newtons being pulled horizontally. The box is traveling at a constant velocity. This indicates to us that the object is in equilibrium. That means the applied force to the right is balanced by something opposing it to the left. And that's your force of friction. Friction opposes motion. So if this is an equilibrium, left and right sides are equal and balanced, opposite direction. So your magnitude of the frictional force is the same as the horizontal component of the applied force. That's 130 newtons. All right, and then 74 to 75 will now have us calculate the magnitude of the normal force, which we can calculate through the frictional force. So now our answer from 73 carries over to 74 to 75. So as long as if you put down an incorrect number, as long as you know that it's going to be used for the next problem, that's correct. You still get points for the 74 and 75. So the equation is FF equals mu, F of N, that's the normal force. 130 newtons is our frictional force. The mu value, we have to look up on our reference table, and I'm going to pull that up in a second. Alright, so here's our reference table. The coefficients of friction are listed for us. Our material that we're focusing on is wood on wood. And there are two types of friction, kinetic and static, but because the object's already in motion, we're going to stick with the kinetic coefficient of friction. So that's 0.3 that we're going to use. Alright, so let me get rid of this. 0.3 is our mu value. So 0.3, no units for the coefficient. And then F of N is our normal force, which we're solving for. And then we get a normal force value of 433 newtons. And that's our answer for 74 to 75. Okay, for 76 to 77, we need to calculate for the car's speed as it travels around the curve. It's going around a circular path. So here's our mass. So radius of 45 meters, that's our R value. And it has a centripetal acceleration of 3.2 meters per second squared. That's A subscript C. We need the speed, V. So there's one equation that fits our given information. That's AC equals V squared over R. And we have our given values, 3.2 meters per second squared equals V squared divided by 45 meters. Do not forget to take the square root in the end so that we can figure out what V is. You get that velocity is equal to 3.79 meters per second as your speed. 78, determine the magnitude of the centripetal force, and that's FC. You could calculate it using MAC, which we all have anyway. You don't have to show work, but I'm going to show you what's required to get the answer. Or not required, but how to get there. You just take your mass multiplied by the centripetal acceleration, 3.2 times 1500. And that'll get you 4,800 newtons as your answer. You just need to put 4,800. Okay. Now 79, what force provides the centripetal force needed for the car to travel around the curve? There are multiple answers that could fit under this. So when a car travels around oh, that's an ugly circle. As best as I can. So here's your object, the car. Centripetal force points towards the center. So as it's traveling around the circle, there's something that pulls it in. So what keeps you from falling out of the circular path? And that's friction. The most common answer that applies here is friction. But other acceptable answers are electrostatic force, etc. But the most common one accepted answer for this question is friction. Because friction is what keeps you traveling inside the circle. Once it gets slippery with less friction, then you're likely to steer out of control, but with the higher the friction, then the more likely you're able to stay within the circular path. So think about slippery surfaces versus non-slippery surfaces. Okay. Number 80. Describe what happens to the magnitude of the centripetal force as it travels around the curve if the speed decreases. So I like to use equations to help me figure out relationships between variables. So here we could see a direct relationship, but more specifically an exponential quadratic relationship between centripetal force and velocity, speed, because it's squared, and that's how these two are related. It's more of an exponential quadratic relationship. One goes up, the other goes up also. So if speed decreases, so will the centripetal force. So all you need to say is that it decreases for your answer. Alright, 81 to 85, here we have a musical instrument with a string 0.62 meters long at its two fixed ends. You pluck it and it vibrates to the musical note called G with a frequency of 196 hertz. So this is your F value. And it looks like my tablet needs to be restarted. Okay, let's ignore that for now. 81. On the diagram of the standing wave in your answer booklet, label one node with N and one antinode with letter A. So I'm going to put this in red. The node are these two fixed ends, those 2 points that look like they're staying in the spot. So you could put that or that. Either one's acceptable. And then the one that vibrates up and down at maximum displacement amplitude, that's antinode, right there. So the two fixed ends here and here are the nodes, and then this part of the wave that vibrates up and down for a standing wave is the antinode. Okay. Number 82, determine the wavelength of the standing wave on the 0.62 meter long vibrating string. So in our case here, we have a string that looks like it shows a standing wave that's half the wavelength. That's what I'll tell you. So this wave is half a wave. Wavelength I like to use by definition as meters per wave. And if you have 0.62 meters over half a wave, you have to double it, and you get 1.24 meters as your wavelength. Because if you continue to draw this out, if this is half a wave, the other half would expand out this way, being twice the distance of what you see. Okay. Number 83 to 84, calculate the speed of the wave traveling on the vibrating string. We have to show all work. So here's the equation, V equals F times lambda, wavelength. We're calculating for speed. Our frequency they give us is 196 hertz times a wavelength of 1.24 meters. And you get your answer to be 243 meters per second as your answer. And then 85, describe what happens to the frequency when the musician shortens the vibrating portion of the string by pinching the string against the fingerboard while the string continues to vibrate. So speed will stay constant. It's still vibrating along the same string, so nothing changes with its speed. Speed only changes when it goes through different materials, different medium. Now that means frequency and wavelength are going to vary with each other inversely. If you have a music background, this might be easier for you, especially when you play string instruments. The shorter the string, the shorter you fix your string with two fixed points, the higher the note. So when the musician shortens the string, the wavelength goes down. And as a result, the frequency will increase. So for your answer, you're going to say frequency increases. And that's it. That's the end of this Regents. So I hope this was all helpful for you. Please make sure you go back to all 4 parts if you ever want to go through any of these questions again. Feel free to check past years' editions of these videos. And yeah, good luck to everyone taking the Physics Regents on June 25th. See you then.